Hello, my name is Amy Blythe and I'm with Tri-Hydro Corporation. I'd like to welcome you to our presentation today, Efficient LNAPL Site Management Using NSZD. Today, our three speakers are Lloyd Dunlap, who will be covering the effective application of NSZD, Louis Rochini, who will be discussing a case study using NSZD at a former refinery, and Ben McAlexander will talk to us about NSZD rates and site characterization. Before we get started, I'd like to go over a few housekeeping items. This webinar is being recorded and will be available via our website after the webinar. All attendees are in listen-only mode. If you have questions at any point, please use the question tab in your GoToWebinar attendee panel. We'll save time at the end of the webinar for Q&A after our speakers have presented. If we're unable to address any questions in our hour together, we'll answer them via email after the webinar. Also, in your GoToWebinar attendee panel, we've included a copy of today's presentation in the Handouts tab. Finally, you will have an opportunity to complete a very short survey when you exit the webinar. It will take just a minute of your time, and we hope you can participate as your responses help us create valuable webinar experiences for you in the future. Also, please place your topics you'd like to hear about in the future for webinars in the questions panel. Now, let's get started. Today, we would like to give you 1 hour on benefits of measuring NSZD at your site. We will cover NSZD, what it is, and how do you measure it at your site, the benefits of better site management through NSZD, and why you should consider NSZD and including it as a component of your remedy, or in some cases, the primary remedy at your site. With that, I'd like to introduce our first speaker, Lloyd Dunlap, professional geologist, hydrogeologist at Tri-Hydro. He is an instructor for the popular Interstate Technology and Regulatory Council, ITRC, LNAPL technical guidance document. Since 2018, he has taught over 3,000 webinar participants on the IRTC approved remediation techniques, one of which is NSZD. Mr. Dunlap has successfully advocated the use of NSZD to multiple clients, plus state and federal regulators. Mr. Dunlap has over 35 years of experience with RCRA for active and closed refineries, public relations, advocacy with regulators at EPA headquarters and states, organizing teams for strategic solutions, facilitating senior level strategic planning sessions, project management, and public speaking. Lloyd will be sharing insights with us on effective application of NSZD. Lloyd, with that, I'll turn it over to you.
Okay, well, thank you, Amy, and welcome everybody. So like Amy said, what we're going to cover today is just the effective application of NSZD. How do you use NSZD for your site management? We're going to give you some actual examples from refineries that we worked on. We're going to talk about at the end the key benefits and the takeaways that we think are the benefit for NSZD. And then, like Amy said, we're going to have time for questions and answers at the end. You want to go to the next slide? Okay, so what exactly is natural source zone depletion? Now, this is a diagram from the ITRC guidance in 2018. So NSZD processes are the example of volatilization, and dissolution, and biodegradation. What happens is they reduce the LNAPL mass, saturate, and mobility over time. Now, LNAPL, as you know, is really the acronym for light, non-aqueous phase liquids, such as petroleum, what we have here. We're going to talk about today. And number two, NSZD is a way to measure and demonstrate that rate of hydrocarbon removal. So NSZD is basically just measuring that rate. Now, NSZD is not new. It was first talked about by Johnson and others back in 2006. He used the chemical gradient method. He measured vapor in wells for methane and CO2 and oxygen. And then ITRC discussed NSZD back in 2009 in their guidance document. And then in 2011, Scioto and others talked about NSZD CO2 fluxes by the chamber method. And most recently, we have seen increased regulatory acceptance of the concept of NSZD. Next slide. Okay. Now, we'd like for you to think about your conceptual site model and how effective the application of NSZD into your conceptual site model. Now, we'd like to think of our conceptual site model in 3 different phases. The initial phase, your initial CSM, your remedial CSM, and also your performance CSM. So how can you use NSZD? Well, number one there, you can use NSZD as a benchmark to measure the effectiveness and the efficiency of your current remedial systems that you may have at your site already. And number two, NSZD can be that final step in a remedy treatment train to achieve the remedial objectives for the site. Or number three, NSZD can be your primary remedy for a portion of your site, especially if you have large sites. And number four, NSZD can be as a component of the remedy at a site. And number five, NSZD can even be your final remedy for the entire site where the risks are managed and are acceptable. So you can see you need to have a good understanding of your remedial CSM and your performance CSM, and where does NSZD fit in, if at all? Okay, next slide. Okay, so let's focus on the effective application of NSZD, and this time in your remedial CSM. And what you can do is you can take a look, is NSZD reducing the mass within your LNAPL zone to achieve LNAPL stability? For example, do you still have a migrating plume, or is it stable? Also for your dissolved plume, is it migrating or is it stable? Number two, are NSZD processes in the LNAPL zone, are they achieving the mass losses comparable to, or even better than your current remedial systems at your site? And we'll talk more about that in just a little bit and give you some examples. And number three, is natural attenuation in NSZD mitigating the migration of your dissolved hydrocarbon plume at the site? So this is a picture of collars used in the for measuring NSZD using the dynamic closed chamber. And Ben's going to talk about that here in just a few minutes. The next slide. So these are our trihydro perspectives. Now, many regulators consider NSZD a viable remedial approach, and I know we have several regulators on the call today. Now, number two, NSZD is acceptable only if receptors are protected. And of course, that goes with any engineered remedial system. Are your receptors protected out there? Number three, NSZD is a good option when the existing engineered remedy is approaching an endpoint. So as we know that some active remediation systems are just going to have to reach this technological endpoint, and it's going to end. Now, NSZD may be a good option to when your existing engineered system is reaching an endpoint, but stakeholders are looking for justification to continue something instead of completely transitioning out. NSZD may fit in that aspect. But NSZD is most accepted where all stakeholders, including your regulators, already see the large LNAPL body at a site as something that's pretty intractable, that is a tractable problem that will not go away. NSZD may be a good option to look at. And number four, often NSZD is not the sole remedy for an entire LNAPL site early on. Now, we think that you should be measuring NSZD early on, but most often on your first part of your active recovery for your remedial CSM, maybe NSZD is not the only thing going on out there. Active systems may be going on also. And number 5, hotspot remedies can be enhanced NSZD. What I mean by that there are people out there looking on ways to enhance NSZD. People are looking at warming blankets, gypsum, low air pulsing, or low air venting. The picture of the windmill is actually a trihydro site where we are pulsing air into the system, into the subsurface to enhance the NSZD. Okay, next slide. This is some things at trihydro we've learned. Now, some states out there have an MNA fact sheet that regulators use to reference when accepting a transition out of active remediation, an MNA fact sheet. Now, trihydro has shown that in some of these cases, NSZD meets each of the criteria in that MNA fact sheet. In other words, we're using the MNA fact sheet as an explicit checklist for them. Now, many states have been amenable to using NSZD as justification to shut down inefficient remediation systems. Using number 2, using NSZD in a residential area, so long as the receptors are protected, such as groundwater use is restricted, or there's no problems with petroleum vapor intrusion. And lastly you can also use NSZD as a site-wide remedy for large LNAPL sites. We've actually seen that. Such sites may have localized active remediation systems that will phase out and transition all to NSZD. Okay, all right. You want to, next slide, please. Okay, so here's an example of using NSZD in your performance CSM. The top pie chart and bar chart is from an actual site. And for a 50-acre comparison, what we did, we went to the interior of a site at this former refinery and measured a 50-acre comparison. Now, we found out that NSZD in this 50-acre area was reducing approximately 240 kilograms per day. Now, adjacent to this, there was an active SVE system going on. And this SVE system also had a comparable footprint of approximately 50 acres. Well, that SVE system was removing 38 kilograms per day. And in the center one there, the groundwater bioremediation, hydrocarbons were being lost in there for bioremediation, approximately 5 to 10 kilograms per day. So you can see here in that chart on the upper right that predominantly NSZD was removing more mass at that site than the active remediation system. Now on the upper left, this pie chart here, this is simply another way to show it on how you compare the removal of LNAPL mass from NSZD to removal by SVE. And you can see there, this is just a way to show that your predominant removal is by NSZD. Now, if you look at the bottom of this, the pie chart and also the bar chart, this is 2022. Certainly, this is just a hypothetical way of looking at it for a performance CSM. But as we all know, that remediation systems, especially as they get older, tend to reduce their effectiveness year by year until it is really not technologically available to actually continue to even use them. So if we assume that the SVE system continues to decrease in the amount they recovered, and that the NSZD, being thought to be a 0 order of magnitude, stays the same, the pie chart on the left shows you that if you would compare year by year by year, that pie chart would become increasingly more LNAPL loss by NSZD than the active system. We only show you this because this may be a very good way to show and demonstrate the effectiveness of LNAPL mass loss by NSZD compared to your active systems. It'll paint a good picture for you and your stakeholders to show how NSZD is removing compared to your active system. Okay, so Amy, I'd like for you to bring up the first poll. Okay, so here's a poll we'd like for you to answer. You can be clicking on this. In your opinion, how significant a role does NSZD play at your petroleum hydrocarbon sites? Either insignificant, potentially significant, significant, or I don't know much about NSZD. Go ahead and answer those.
All right, it looks like we have a majority of our folks that have voted, so I'm going to go ahead and close the poll, and then I will share the results with you all. And Lloyd, the way it's looking, we have a majority of folks, about 41% said significant. Looks like 39% said potentially significant. 20% said, I don't know much about NSZD. And then we didn't have anybody say insignificant.
Okay. Well, thank you very much for that. Thank you.
All right, so appreciate all the information, Lloyd. And I think now it's time to hand it over to Ben, or excuse me, Lewis, my apologies. Just a reminder for the folks on the phone, we're holding questions until the end. So if anything Lloyd covered sparked a question, please submit your question in the attendee panel at any time. Next up is Lewis Rochini. Lewis will discuss a case study at a former refinery in Wyoming. A little bit about Lewis. He has 28 years of professional experience in environmental consulting, serving as a project manager and a senior hydrogeologist. His primary responsibilities have included designing and implementing soil and groundwater quality assessment and remediation programs, evaluating the contaminant environmental fate and transport, remedy evaluation, and construction and operation and maintenance of long-term soil and groundwater remediation projects. Mr. Rochini has also participated in negotiations with regulatory agencies and has provided oversight for closure of a number of petroleum release sites and chlorinated solvent release sites. And with that, Lewis, I'll turn it over to you.
Okay, thanks, Amy. We're going to look at another example of a former refinery where Tri-Hydro has demonstrated the effectiveness of NSZD to the regulatory agency. And I'll start by providing some site background and general LNAPL information for context. You're looking at an aerial photo here from 1947. You can see the former refinery. It has an orange outline, and it's approximately 30 acres. The property to the south of that, with the purple outline, is a former tank farm that's 55 acres. Only the northern portion of that is shown. So the refinery operated from 1917 to 1956. The tank farm pumping station started a little bit later than the refinery, but operated through the mid-1990s. Next slide. All right, so here we're looking at a footprint of the smear zone or LNAPL zone that resulted from releases from the former refinery and pumping station. It's approximately 134 acres, so pretty sizable. And it's the maximum historical extent is really what you're seeing here. So you can see the refinery outlined again in orange there, just for scale and for orientation of how the LNAPL zone relates to the refinery and pumping station. You can also see a black line on the northwest corner, or outside of the northwest corner of the former refinery, and that is a LNAPL recovery trench system. I'd also point out that there's a river right at the top of the map there. You can just see the river where the LNAPL plume eventually reached. So the trench on the northwest corner of the refinery has been operating for 16 years, and recovery is waning, as the Performance CSM predicted. The topography of the land slopes downward to the north toward the river, and obviously, or predictably, so does the hydraulic gradient. So when LNAPL was released, it migrated generally north toward the river until at some point it reached it historically. The project actually started in 1994 when a sheen was observed on the river, and it began under EPA. The smear zone that you're looking at was delineated using Ross probes and well borings primarily. The color ramp on that smear zone indicates thickness. So the outer edges where it's green is 1 foot, and in the interior where it's red, it's approximately 20 feet thick. The composition of the LNAPL, it's a mixture. It's a blend of petroleum intermediates, diesel, gasoline, other fuels that were produced. Okay, next slide. The current LNAPL plume is shown in green, in light green on this slide, and it's approximately 30 acres. But that can vary with water table fluctuations. As the water table goes up, the mobile LNAPL tends to decrease, and the plume appears to be smaller. And as the water table goes down, it appears to be larger because mobile LNAPL enters the wells, and that's what this figure is showing, is mobile LNAPL that's measured in wells. The maximum recent LNAPL plume that we've seen has been about 70 acres. The one, as I said, that's pictured here is about 30 acres. So this maximum LNAPL plume is approximately half the size of the smear zone, indicating that in the preceding decades, since the refinery closed, substantial depletion of mobile LNAPL by NSZD processes in the smear zone has occurred since its maximum extent. So this is a pretty huge reduction. And granted, it does take some time, but it really illustrates well what NSZD is capable of. So knowing that we'd want to NSZD to be part of our remedy at this site and considered by the regulatory agency as a significant component of the overall site remedy, we began monitoring for NSZD in 2018 before the remedy agreement and remedial action plan for the site were prepared. During remedy discussions with the regulatory agency, regulators were interested and open to NSZD being incorporated into the remedy agreement and remedial action plan because they understood its potential for high rates of depletion in source areas and that it would be effective for residual LNAPL when other active remedies would not be. Next slide. All right, so the overall objective for collecting NSZD data is to provide the necessary information to decision makers to allow them to manage the site remediation in the most efficient manner possible, which is very important when you have a site that's large. More specifically, though, the objectives include characterizing and quantifying NSZD at the site to allow for efficient site management. It's important to quantify degradation rates and volumes so that NSZD can be compared to other potential remedies, whether those are existing remedies, existing systems, or other possible remedial options for the future for the site. Once NSZD has been characterized and quantified, we can understand what its role in the future remediation of the site could be. It might be only one component, as Lloyd mentioned earlier, of the site remedy, along with one or more other kinds of active remediation, or it could be the sole remedy if plume containment and other conditions are met. In any case, having NSZD characterized and quantified gives the decision makers the information that they need for effective site management. At this point, I'm going to turn it over to Ben to discuss some specifics about NSZD collection, NSZD data collection and interpretation.
Thank you, Lewis. Again, don't forget to enter your questions in the questions panel on your GoToWebinar pop out. Now, Ben McAlexander will share NSZD results for this case study. Mr. McAlexander is a contaminant hydrologist for Trihydro. His primary role is development of site conceptual models at petroleum effective sites and their application to management decisions. He conducts remedy performance monitoring on hydrocarbon attenuation processes, including NSZD and green enhancements to natural hydrocarbon losses. He regularly publishes his work in academic journals and presents at environmental conferences. Ben, we look forward to hearing more.
Thank you very much. Lewis set us up with context for this case study of a large former refinery and why NSZD data were collected. I'm now going to talk to you about, on the next slide, how were NSZD data collected for that site, how are they converted to hydrocarbon removal rates, and how are we using that data? So we will start with, on this next slide, what are some methods for measuring NSZD rates? We have 4 that are shown on this slide. The first one, number 1, is a concentration gradient method. This is where we place soil gas probes in the subsurface and measure profiles for gases like methane, oxygen, and CO2. The reason we do that, it gets back to the conceptual site model that Lloyd introduced, where hydrocarbons, LNAPL, in the subsurface, those hydrocarbons are lost from the LNAPL over time, and a lot of that occurs by biodegradation. In the area near an LNAPL body, a lot of that degradation is by methanogenesis. So if we see methane showing up in soil gases near the LNAPL body in the Bedos zone, then that's a good indicator that NSZD is occurring. As that methane moves upwards in the subsurface, eventually it contacts a zone where there's a good amount of oxygen, and their aerobic microorganisms are able to consume that methane and maybe other hydrocarbons, and that generates carbon dioxide. So if we see decreasing oxygen concentrations with depth, or we see increasing CO2 concentrations with depth, we can use those profiles or gradients in those gas concentrations to estimate an NSZD rate. So that's one method we can use to do that. Also, all of that CO2 that is generated in the subsurface by hydrocarbon biodegradation, it's got to leave somehow. It's got to leave the subsurface, and when it does, it leaves the ground, and you can measure that rate of CO2 exiting with passive flux traps. That's number 2 on this figure here. These are sorbent media that can collect CO2. You place them out in the field and they sit for about 2 weeks or so, and you can then send the trap off to a lab and they can quantify the amount of CO2 that came out of the ground. If you can quantify the amount of CO2, then you can estimate the amount of hydrocarbon degradation that was associated with it. There's also the dynamic closed chamber. That's number 3 on this slide. That also measures CO2 coming out of the ground, but it's a real-time measurement. It's an instrument that you can carry around your site, measure CO2 fluxes. And instead of being a 2-week measurement, it's a 2-minute measurement. So you can get a lot of samples in a short amount of time with the dynamic closed chamber. And then finally, there's the biogenic heat method. With all of that methane getting degraded aerobically in the subsurface, that generates a lot of heat. And so you can measure the heat signature and convert that over to a hydrocarbon attenuation rate. So there are 4 methods out there. For this site, we use item 1, item 3, and item 4. And for this example we're going to share with you, we're going to emphasize item 3, the dynamic closed chamber. So on the next slide, here's why we're emphasizing the dynamic closed chamber. Like I said, because it's a 2-minute measurement, you can get a lot of measurements in a short amount of time. And Lewis mentioned that the full LNAPL zone, the smear zone for this site is large. And so we went ahead and gridded up the site and we got a lot of CO2 efflux measurements over that full LNAPL zone footprint. And you can see those little points on the figure on the left here, as well as color flood of the CO2 efflux measurements with higher fluxes as darker colors. So what we saw when we did this, we measured site-wide fluxes in 2018 and 2020, and we're showing 2020 data here, is that we got a good range of measured fluxes, from less than 1 micromole of CO2 leaving the ground per square meter per second to more than 10 micromoles per square meter per second. So it's a good range. We also went to a background area of the site and we measured CO2 effluxes there. The reason we do that is because just plants in the ground, their root zones also exhale CO2. So we want to measure the CO2 effluxes in a background area to compare it to what's occurring over the LNAPL zone. So we have a feel for the additional CO2 efflux, which is the indicator of the NSZD rate. What we saw in that background area was that the fluxes were less than 3 micromoles per square meter per second on average. So that's a lot lower than what was measured over the LNAPL zone. And so that does point to hydrocarbon biodegradation occurring over the LNAPL zone. We can subtract the background CO2 efflux from the value, the average value that was measured over the LNAPL zone, and then we can convert that over to a hydrocarbon biodegradation rate. And what it comes out to is 690 gallons of hydrocarbons, or LNAPL, being removed per acre per year. That's a lot of hydrocarbons being lost by natural processes over 1 acre. But this is a big site. It's 134 acres for the LNAPL zone footprint. And so over that big footprint, it's even more hydrocarbons. It's more than 90,000 gallons of hydrocarbons being removed in a year. So that sounds like a lot. It is a lot. The LNAPL recovery trench recovered in that same year, 2020, about 4,800 gallons of LNAPL. And so over the full footprint of this LNAPL zone, a lot more hydrocarbons were removed by natural processes than were removed by engineered remediation. So on the next slide, we can see, well, how can we use this for site management? One way is we can start breaking up the data into specific parts of the site and seeing how things shake out. So Lewis emphasized that LNAPL recovery is occurring at this site, and that there is an area of the site where LNAPL does enter monitoring wells, about 30 acres in 2020. So we went ahead and put that as a dashed pink line on the map on the left side of this slide, that's the zone where LNAPL is entering monitoring wells. And you can see the little black bedrock recovery trench. That's where NAPL is recovered. We can look at CO2 effluxes there versus the site LNAPL zone. So what we see on the bar graph is the site LNAPL zone, the full average CO2 efflux is about 4 micromoles per square meter per second being lost. That is greater than background. So as a whole, the LNAPL zone is removing hydrocarbons. It's higher than background. But in the area where LNAPL enters monitoring wells, the CO2 fluxes were even higher. They're higher than background. They're higher than fluxes over the site as a whole. And so that's helpful because that's the area where LNAPL is in wells, and probably we have more of a source for hydrocarbon degradation and we get those better fluxes. But currently the site is being remediated by that LNAPL recovery trench. And as Lewis mentioned, the recovery from that trench is getting lower and lower as time goes on. We now that we have collected this data understand that that's not the only remediation that's occurring. While active remediation is removing hydrocarbons by LNAPL recovery, natural processes are also removing hydrocarbons, and they're removing a lot of them. They are a part of the remedy now, even though we didn't realize it before. But also looking into the future, eventually that NAPL recovery trench is going to not really be able to get much more NAPL out of the ground. And yet NSZD will probably continue to occur. So NSZD is a part of the remedy now, and potentially in the future, it could be the sole remedy for this area. So that's one way you can look at this sort of data is this place where NAPL enters wells. On the next slide, we look at another important part of the site. This is the alluvial part of the site that Lewis talked about, the area adjacent to the river. LNAPL does not enter wells there anymore, but LNAPL is still present in the subsurface there as residual. Well, we can look at CO2 effluxes there, and that's what's shown on the bar graph here. You see the middle bar, that's the bedrock smear zone. That's basically where LNAPL is entering wells, and we do have higher fluxes there. But in the alluvial area, we still have substantial CO2 effluxes. They are higher than background. NSZD is occurring there. Hydrocarbons are being removed by those natural processes. And that gives us some understanding of why NAPL isn't entering the river anymore. There was a time when NAPL migrated to this area. The releases were to the south at the former refinery and even further south of there. So NAPL is able to migrate, but it is not migrating now. It really doesn't even enter monitoring wells there now. And that LNAPL body stability is achieved, at least in part, by these hydrocarbon removal processes that are natural. So that helps us understand what's going on there. And currently, we don't have an active remedy for this alluvial area. The NSZD data provide evidence that perhaps this could be the case long term. So that was an example of how some NSZD data can be used to start looking at site management. And on the next slide, we hope that it emphasized a few things about benefits of collecting NSZD data. One is that NSZD often outpaces mechanical LNAPL system recovery for late-stage LNAPL sites. That's been our experience, is that especially when you look at the full footprint of hydrocarbon impacts and count those hydrocarbon losses that are occurring naturally, that they are substantial. And if you've got a system that's not really getting a lot of NAPL out of the ground, that's an engineered system, it might be beaten by NSZD. This was a former refinery. It's not operating anymore. We work a lot of those sites, but we also work operating facilities, large refineries, pipeline sites, and our experience is that NSZD is occurring at those sites as well. And it can occur pretty soon after a release occurs. We've been to I can think of one pipeline release site where we got out there within a year after the release occurred and measured CO2 effluxes there versus a background area. And that place where NAPL was in the subsurface had higher fluxes. NSZD had ramped up pretty early on, and that helped us understand what was occurring naturally and what remediation options were. Not that NSZD was the sole remedy at the beginning for such an early site, but at least we had a full picture of what was going on. Also, this site that Lewis introduced to us has 4 seasons, and 2 of those seasons are really cold. NSZD is occurring even then. We've seen this at that site and other sites that in the cold parts of the year, that hydrocarbon attenuation, even biodegradation, is occurring. It may not be as fast of a rate as when it's warmer out. Microbes that consume hydrocarbons do respond to temperature, but it is occurring in the winter. And if you want to characterize that seasonal variability, you can go out each of the seasons and measure those rates. But also, if you're interested in just measuring a site-wide annual average NSZD rate, we have found that going out in one of those moderate seasons, especially the fall, is a great time to go out and measure and get an approximate indicator of the annual average NSZD rate. And then a final benefit of measuring NSZD rates is this was baseline for this facility, understanding what hydrocarbon removal is occurring naturally. If in the future hotspot remediation is desired, the same types of measurements can be taken to know whether additional treatment has an effect. If you add oxygen to the subsurface and it increased hydrocarbon attenuation rate, it will generate heat. It will increase CO2 generation and effluxes, and you can measure by these same methods. So it's useful for measuring enhanced NSZD. So on the next slide, before we get to our next poll, we are often asked, what about the cost of NSZD measurements? So we wanted to give you some ideas about that, and first just list out some factors that can affect the cost. So these are factors for sites that aren't just like a simple little UST site. So a moderately large or really large site, those are really the types of sites that we tend to work. And factors that we have found to be of import include, are you trying to measure an annual or a site-wide NSZD rate, or can you get sufficient data by going to stations and measuring NSZD in localized areas? If you can just find key parts of your site and confirm that NSZD is occurring there and measure those rates, then that can help you get the cost down because you're not doing site-wide evaluation. That's especially the case for some of those subsurface methods that can have where you have to install monitoring infrastructure, set up stations. Another is what frequency of monitoring is needed. As I mentioned, if you have a site with multiple seasons, you may want to go out each season and measure NSZD rates. That can affect the cost. But even if you're going out site-wide and getting trying to get an annual average, if you go out, say in the fall, you may get a good estimate of the annual NSZD rate. And then a final factor is, how many methods are you going to use to measure these rates? We tend to use more than one method at a given site because we want to have multiple, we want to have confirmation that what we're measuring by one method does align with what is measured by another independent method, and it gives us more confidence. It's that whole idea of multiple lines of evidence. But of course, when you use multiple methods, that means a higher cost. So with those factors in mind, we can say that it is our experience that a cost for a baseline assessment of NSZD rates could be in the $10,000 to $50,000 range for baseline, and maybe could decrease thereafter. Maybe sometimes more than $50,000, maybe sometimes less, but that's just a ballpark that we've seen over time. So now we get to see our next poll question. And it is. What are your concerns with using or considering NSZD for your sites? So it's multiple choice, but you could get to check all that apply.
All right, looks like the votes are coming in. We'll close it off in just a few seconds. All right. Thank you everybody for participating. I'll go ahead and close the poll right now and then launch the results. Okay, so it looks like we've got about 13% of people interested but not familiar and need to know more. We've got 17 that are uncertainty of long-term results, 4% as NSZD is insignificant for the site needs for cleanup, 35% time to reach cleanup is too long, and 31% I have no concerns using or considering NSZD. All right, with that, I'll pass it back to Lloyd to wrap us up today.
Okay, thank you, Amy. So, so anyway, why is NSZD not used at more sites? Remember that NSZD was first promoted back in 2006 by Johnson and others. Now, last year, Jacobs did a similar poll question that what we just did, and they presented it at a REMTech conference. So the top 3 answers, and the people who participated in the poll there were 44 of them were consultants, there were 4 site owners, and 2 regulatory staff. And the top answers that they gave last year, regulatory hurdles are present. Perception is that NSZD is slow, passive, and insufficient. And that was kind of indicated on the poll we just did. Or they are unfamiliar with NSZD. There were several answers, but these were the top 3 that the REMTech webinar series promoted. So anyway, the thing is though, we want here at Tri-Hydro, we want to continue to tell the story about NSZD. We have found that regulators are becoming increasingly more interested to, or will consider NSZD, which is kind of what we saw in our poll also. We have found that it was mentioned slow, passive, and insufficient, but we have found that NSZD LNAPL removal rates can be quite large compared to an active system, which we showed you there. And talking about unfamiliarity with NSZD, we just hope that these webinars and other conversations we have can increase familiarity with NSZD and why it should be at least considered for your site. Okay, next slide. So let's talk about things to consider when using NSZD. We're kind of wrapping it up here in the key takeaways. Number 1, you want to evaluate the risk to receptors. But that's the case when using any technology. Just understand what the risk to receptors are. Number 2, you want to understand and monitor the progress of LNAPL mass removal. That means some of the pie charts and bar charts that I showed and Ben showed, just understand and monitor the progress of NSZD, and maybe you can even do it just annually. Number 3, you want to compare the NSZD removal rates with your other active remedies at the site. You may be surprised how much NSZD is removing compared to your active remedy like we showed you. And number 4, so NSZD typically occurs across the entire site where LNAPL exists. That means even though you have sites where you don't have an active system, NSZD is probably occurring all across your site where you have LNAPL in the subsurface, either through residuals or even in monitor wells, measured in monitor wells. So it is important to, it is number 5. So it's important to evaluate the removal rates of NSZD and determine, based on all the factors at the site and your remedial CSM, is it acceptable with the removal rates you're seeing from NSZD? Okay, next slide. Okay, let's talk about some key takeaways here. So you want to think about, we suggest you think about, include early collection of NSZD removal rates. Like Ben talked about, you could have a recent spill, but after just a few months or several months, go out there and find that NSZD is actually already starting to occur. And we're pretty much seeing that, and ITRC is seeing that pretty much all across the country. Number 2, you want to consider the feasibility of NSZD and compare it to your active remediation systems if you have one out there. Number 3, we suggest that you consider identify early on if NSZD is significant and that if your risk to receptors are acceptable. And number 4, we suggest you think about including NSZD in establishing exit points for your remedial and performance CSM. So what do I mean by that? Well, maybe you want to establish with your stakeholders, including your regulators, a decision diagram on what conditions would be out there that you would start considering NSZD as at least a component of your remedy or even your entire remedy, just depending on what those decision trees are. Very good exercise to do up front and get agreement with your stakeholders and regulators on what those might be. Okay, next slide. So here are our high-level perspectives of the benefits of NSZD as a remedy. Number 1, you want to understand your cost and benefit differential of NSZD compared to an active system. What is the cost for NSZD measurement compared to operating your active system? And number 2, like Ben talked about, NSZD is easily measured and easily monitored, and you may even be able to get by with monitoring once a year in the fall, like Ben mentioned. Number 3, NSZD is only one of a few remedies that's going to remediate LNAPL residuals. And possibly, if you're trying to remediate LNAPL residuals, unless you have an extremely small site, NSZD is possibly the most cost-effective. And also, with NSZD, your LNAPL mass is reduced in the subsurface without having to manage recovered groundwater and LNAPL from active systems. This doesn't even mention the possibility of having to manage any excavated soils out there. Okay, so make sure when you have this, though, just make sure that it's approved by all your stakeholders. Okay, number 5, next slide. So here are our parting thoughts. If you manage the site with LNAPL, do you know the amount of LNAPL mass that's actually being removed by NSZD? And if so, how does that compare to your active remedial systems? The next one. Another parting thought is, should you include NSZD at least as a component of your remedy along with your active systems? Okay, and the next one. Okay, so that is it. Amy, I'll turn it back over to you.
Great, Lloyd, thank you. Now let's move on to our Q&A. We have a couple minutes left together. Thank you for all of those people that have submitted your questions. And if you haven't done so already, please feel free to put them in the questions panel. And if we don't get to them during our time together, we'll be sure and follow up with an email. Our first question is for Ben. How is NSZD different than MNA?
Okay, so I am on an ASTM standards committee that's writing a guidance document or standard for NSZD measurements. And in the definitions section of that document, there's going to be one for MNA and for NSZD. So the answer I'm about to give you is what that standard will say. MNA, monitored natural attenuation, is a broad or umbrella term. Natural attenuation occurs to LNAPL, it occurs to hydrocarbons in soil gas, it occurs to hydrocarbons in groundwater. NSZD is focused just on attenuation or hydrocarbon removal from the LNAPL. So from that perspective, NSZD is one type of natural attenuation. And if you're monitoring NSZD, it will be one part of MNA. Now, historically, most people, when they think of MNA, they think of groundwater, dissolved phase plumes. And so from the perspective of MNA being a broad term, the reason that MNA has typically been applied in the past to groundwater and dissolved phase plumes is because, for two reasons. One is that that is what was measurable in the past. Some of these other methods that we shared with you about NSZD measurements are new, but in the past, people could watch constituent concentrations, hydrocarbons decreasing in groundwater over time, and look at groundwater geochemical indicators of natural attenuation. So that's one reason for the focus on groundwater. Another is that that's where compliance was largely focused. Are we getting to cleanup levels in groundwater over time? And so we focused on that for MNA. But MNA could be applied more broadly, and NSZD then is a type of MNA.
Great, thanks for that information, Ben. For Lloyd, here's a question for you. How does NSZD change the composition of the petroleum, especially on refined products?
Okay, great question. So we are finding, and ITRC is finding in the consortium we have there, that is pretty much all across the spectrum, from the light hydrocarbons to the heavier hydrocarbons. Now, not so much maybe on the very dense hydrocarbons, but if you think about the hydrocarbon ranges in the gasoline, diesel, kerosene area, it seems like NSZD is effectively biodegrading all the straight chain hydrocarbons there, plus the aromatics also. So it's not really specific to any one particular hydrocarbon. It's pretty much all of the hydrocarbons across the chains between gasoline through diesel.
Mm-hmm.
Great, thank you. All right, back to Ben. These are two questions combined. We received a couple similar questions to this one, but did you measure the CO2 flux in different seasons? And the second part of the question was, how do flux rates vary with changes in ambient temperature, barometric pressure, etc.?
Okay, so for this site, NSZD by CO2 effluxes was measured in one season, I believe. Is that right, Lewis, for site-wide?
Well, actually, we did a couple of semi-annual events initially.
I will say that at a site very near here, you can look this up in groundwater monitoring and remediation, maybe like 2019 or something. We looked at monthly CO2 effluxes and compared it to precipitation. This is a semi-arid site, precipitation, temperature, and groundwater elevation. You can imagine that as water table comes up, it might submerge NAPL and make it less degradable. So we did that and looked at it from a multivariate perspective statistically. And the answer for a semi-arid site is that actually precipitation was the main factor that affected hydrocarbon removal rates. Probably because the microorganisms are limited in moisture in the vadose zone. When they get it, they really use it. Temperature came in second. It does matter what the temperature is in the subsurface. They like the warmer weather. Groundwater elevation did not matter. They did not care. The hydrocarbons didn't care whether the water table is high or low, probably meaning that NSZD is occurring below the water table in substantial amounts. Even though methane bubbles out of the groundwater and eventually gets to ground surface, it may have occurred largely below the water table. So that's what has been demonstrated, what we have demonstrated in the past and written up.
Well, thank you, Ben. Great information. Unfortunately, we're reaching our end of time. We do have some more questions that were asked, and like I mentioned, we will follow up with those in an email with our insight and answers after the webinar. At the end of the webinar, when we end our time together, there will be an exit survey. We hope that you can take a minute or so to answer those 4 or 5 questions to help us target our webinars better for you in the future. There's also some time to request one-on-one time with our subject matter experts here. So make sure if you're interested in talking with our guys today on the phone that you let us know that. There will be a link to today's webinar of recording along with the PDF of the PowerPoint that will be sent to you tomorrow. If you'd like to receive a certificate of completion for continuing education hours or credits, please contact us and we'll be happy to provide that for you. Well, a very big thank you to our speakers and a thank you to all of you for joining us today. We hope you join us for future webinars and feel free to include some topics in the questions panel if you'd like to hear about something in the near future. Again, thanks so much.
Yeah, thank you.